All right. So, uh, in the last class, we had talked about reliable data transfer protocols, and we had seen that how using FSMs in different types of channels, we can have, we will have add some functionalities both at the sender side as well as in the receiver side to find that what events will cause what actions and how it can be improved protocol by protocol. So we started with RDT 1.0 and then we went to RDT 2.0 and then we went to RDT 2.1. Okay, so what were the cases? So first case was when we had taken a fully error-free channel, right? Then we took a channel which is having some bit errors, right? So after that, we found out that okay, what happens if we do have bit errors, but the ACK and NAC they can also be garbled with bit errors. So we have seen all these protocols. All right. So today what we are going to do is we are going to again go ahead with next cases. Okay. So today we are going to start with RDT 2.2. All right. Somebody's not muted. Please mute yourself.
India in response immediately into the low post. And Young gets the score. Rejected by Young.
Ayush, Sachdev, yes, if you are not listening to the class, you can always go ahead, just leave the meeting. All right? Okay. So, RDT 2.2 is the one that we are going to talk about today. So, until now, what we have found out is that if, the receiver side receives the correct packet, it sends an acknowledgement to the sender. And if it does not receive a correct packet, so it sends a negative acknowledgement. Okay? Now think from the receiver side. All right. Why should a receiver always, if it is receiving something okay, then it will send an acknowledgement. If it is not receiving something okay, then it will send a negative acknowledgement, right? So if from the receiver side, if you can reduce the complexity a bit more, then it will always be helpful, right? So in order to do that, okay, what is it that we are going to do here? In RDT 2.2, we are going to use only acknowledgement packets. No need to get, the NAC packets because, try to reduce the complexity as much as possible. So what we are going to use here is whatever the receiver is going to receive, it is only going to respond with only ACK packets. All right. Now, you can ask me a question that, if it is only ACK packets, then how will the sender get to know about some garbled or some corrupted packet that has reached the receiver's side? Okay, so that is a question that will come up. So remember in the last protocol, we had seen that, we are going to put sequence numbers even in the acknowledgement packets, right? So here also what we are going to do is, or what the receiver is going to do is that it will explicitly include sequence number of the packet for which it is sending the acknowledgement. So suppose if the receiver is receiving a correct packet with packet sequence number 0, so it will send an acknowledgement back to the sender saying that I have received packet number 0. Okay, the sequence number 0. Now, if the packet receives, the receiver receives the same sequence number packets, that means if it is receiving duplicate packets constantly, then also it is going to send the same acknowledgements with the same sequence number, with which the sender will get to know that, okay, so these acknowledgements are basically duplicates from the receiver side. So maybe I should stop sending these packets with this sequence number. Okay, so this is how the basic chemistry works between the sender and the receiver side. Okay, so now let's see what's happening here. So, okay, in this last line, you can see that it is written that duplicate ACK at sender results in same action as negative acknowledgement. That means retransmit the current packet. Okay. So this is for the case that, suppose a particular packet was sent, and then the packet was lost in between. So the receiver side is still going to send an acknowledgement, or here the packet loss is not happening, here it is an erroneous one. The receiver side is going to send the packet with the previous sequence number, saying that, this is the whatever I have received is erroneous, so I the last correct packet that I had received was with this sequence number. So once the sender gets this information, that ACK with the previous sequence number, so it gets to know that, um, the packet that it has been sending to the receiver side is not the correct packet. So that's when it decides to retransmit the current packet. Okay. So let's see how it works out. All right, using an FSM. So this is the sender side. So yes, two states are here. We are still considering the two sequence numbers. So this is for wait for call 0 from above. This is just a part of it, not the full of it is has been given, because next part you can always make out, right? Then the other part is wait for acknowledgement for packet with sequence number 0. Okay. Now this is the initial state. That means at the sender side, the sender is waiting for packet for call from the above layer, that is to send a packet with packet number 0. Once that call happens, okay, I hope my mouse is visible to you people. If it is not, then just let me know. Okay. So this action when it happens, sorry, this event when it happens, that is RDT send data. That means there is a call that has been made to create the packet and then send it over the medium. So that's when these two actions are being taken, that is send packet and then UDT send packet. So the packet is created with sequence number 0, the data, and of course the checksum field, because the channel is still an erroneous channel. Okay. Once this packet, okay, is being transferred or is being transmitted over the medium, then the next state that the sender will go into is, remember, it is a stop and wait protocol. So that means once it transmits, it will wait. So it is waiting for the acknowledgement of the packet that it has sent. Okay. Now look at, so let's go for with the positive side first. So suppose a packet is received at the sender side and the packet is not a corrupt packet, and the sequence number of the acknowledgement is also 0. Okay, so it was actually, it had sent packet with sequence number 0, and it is waiting for packet for acknowledgement of that packet with sequence number 0. So once it is getting that acknowledgement of packet with the same sequence number, then everything is fine. It will go to the next state. That is, it will now wait for call for packet number 1 from above. Okay. So that you can make out that later what will happen after this. Okay. So this is what, when something good goes on, that means no error is there in the packet. Now next part is, suppose if there is some issue. Okay. So what is the issue? A packet has been received at the sender side. Either the packet is itself a corrupted packet, or the packet that has been received is having a different sequence number than what was being expected by the sender side. Yeah. So in both these cases, in either of these cases, the action that will be taken from the sender's side is that it will simply resend the packet. Okay, so it will retransmit. So if you remember the previous slide, duplicate ACK at sender will result in the same action as a negative acknowledgement. That means it will retransmit the current packet. Okay, so this is the one that will be taken, that action will be taken. All right. Now, think about the next parts of it. That is, you can do it by yourself. That is, wait for call 1 from above and then wait for acknowledgement for packet number 1. So then you will realize that maybe previously we are having only two sequences, right? 0 and 1. So previously packet number 1 was the one that was received, acknowledgement for packet number 1, right? So that is why it is given that if we get a repeat or a duplicate acknowledgement packet, that is packet with the same sequence number, if is being received at the receiver side, so then the receiver gets to know that there is something wrong and it simply resends that packet. Okay, now let's get to the receiver side. So what's happening at the receiver side? Receiver is only still having one state, that is wait for packet for sequence number 0 from below. Okay, that means from the below layer there has to be a call that should come. All right, so now what could happen from here? Okay, now suppose a packet is received and the packet is a corrupted packet and it also has a different sequence number, sorry, or it also has a sequence number. So either the packet is a corrupted packet or it has a different sequence number. So then it will send a packet, that means it will send an acknowledgement packet which will have the sequence number of the packet that this receiver had received correctly until now. Okay, so the last correctly received packet, that packet sequence number will be sent to the sender side, saying that this is the last thing that I had received correctly. Right now I have not received anything correctly, I'm expecting the next packet to come. Okay, so when this happens, it will still be in the same state, that is wait for call 0 from below. All right, now you know that if a correct packet is received, then of course it will go to the next state, that is wait for 1 from below. Okay, now if that happens, then again you come back to this state. When do you come back? When, sorry, when a packet is received, it is not a corrupt packet and it has the correct sequence number, that is sequence number 1. Remember that here we do have that state, that is wait for 1 from below. Okay, the next state is wait for sequence number 1 from below. So from there, if we are receiving a packet with the correct sequence number, which is sequence number 1, then only it will get to the next state, that is wait for 0 from below. Okay, so now if this happens, this event occurs, then the actions that will be taken are extract the received packet, deliver the data, and send packet, that is make packet act with sequence number 1, and then you go to the next state. Okay, so now we are going to look at a real scenario where we will have, now we are basically building the protocols, right? So this is the one that we are basically looking at, a more realistic scenario, that is RDT 3.0, where your channels will have errors as well as they will allow or they will have packet loss in that. Okay, so it can lose packet, that is data packets also, it can lose, it can also lose ACK packets. Okay, so until now what we have learned that if there are errors, we can use checksum, we can use sequence numbers to find out that whether the packet is getting duplicated or not. And instead of having both ACK and NACK packets, we can simply use sequence number and acknowledgement to just find out that whether the sequencing is correct or not. Okay, and if there is some wrong sequencing, then the action that a sender takes is that it retransmits the packet. Even if the sender finds out, that means whenever the sender finds out that the packet is not received properly at the receiver side, the action that it will take is simply retransmit the packet. So now here in RDT 3.0, we will get to know that it is actually not quite enough to do all of these things. Okay, because still, what is the scenario when your packet is actually going to get lost? Your receiver is totally closed. The last class we had seen that it's like a curtain that has been drawn between the two entities, sender and receiver. They are not seeing each other. They don't know anything about each other. So if sender sends a packet and somehow while moving towards the receiver, the packet gets lost. So there's no way that the receiver will actually get to know that there was a packet that has got lost, and the sender will also just simply be like, I don't know whether the packet has been received at the receiver side or not, right? So that is why checksum, sequence number, acknowledgements, retransmissions, these are helpful for all the other cases that we have talked about. But how can we find out that whether there was a packet loss or not? Okay. So now let us see what happens in case of humans. So if your friend is sleeping and you want to call them, so you just or you want to wake them up, you call them like one or two times, or you just call them once and you wait for some time for them to wake up. If they wake up, great. If they don't wake up, you call them again, right? So that's what happens in this case also. All right. So the sender will basically wait for a quote unquote reasonable amount of time. So now this reasonable is what we need to define, that what is this reasonable amount of time. It's a matter of rigorous research, that what's the reasonable amount of time between a sender and a receiver. But we need to wait a reasonable amount of time for acknowledgement. Okay. So if the sender gets the acknowledgement within the given time, then great. It gets to know that whether the packet was correctly received at the receiver side or it was erroneously received at the receiver side. If not, then it will just think that the or it will just assume that the receiver has not received the packet, or somehow the packet has been lost in between, so it starts retransmitting that packet. Okay. So now the question might come that we are talking about a very huge network, very it's like a web of so many connections that is going on. So what if the packet is actually delayed rather than it has got lost? Okay, so that means suppose the sender had to wait for 3 seconds before it would start retransmitting. The packet reached the receiver side only at 5 seconds time. Okay, so you can imagine that once, because sender does not know na that what happened to the packet that was sent, so receiver will simply receive that packet. Okay, and now what has happened after 3 seconds, the sender has already sent a duplicate packet once again, thinking that maybe the receiver has not received the packet. Okay, so this will be a problem that we have to see, that how to handle this situation. Now how do we handle this kind of a situation? We already know that every packet we are having a sequence number. So if we have a packet, or if we receive a packet with the same sequence number, that means it is a duplicate packet. So now the receiver will send the corresponding acknowledgement saying that okay, this is, I mean, it's not saying that it's a duplicate packet, it will simply send that information to the sender side, or it will simply drop the packet. Okay, if it sees that there are duplicate packets, it will simply not consider it for decapsulation for the upper layers, because it's not needed. The correct packet has already been received. Okay, so that is why what we are doing is that the receiver must specify sequence number of packet for which it is sending the acknowledgement number. Okay, all right. So yes, so this reasonable amount of time, we call it as a timeout. Okay. So basically the timeout is the time for which the sender will actually wait to receive an acknowledgement from the receiver's side after it transmits a packet. Once the timeout is gone, or once the timeout is over, then it will simply retransmit that packet. Okay. So this is the FSM for the sender side. So the initial state, it of course, a state is of course, the wait for call 0 from above. So now, yeah. So these are the two sets: wait for call for 0, wait for acknowledgement for 0. Okay, and then the next set is the one with sequence number 1. Okay. So now let's see how it works. So first is wait for call 0 from above. So that means when the call for making a packet comes from the application layer side, so then the packet is made with sequence number 0, the data and the checksum, and then the packet is sent. The moment the packet is sent, along with that, there's one more action that is taken, that is the timer is started. Okay. Now, once the timer is started, the sender, of course, will now wait for the acknowledgement. It is a stop and wait protocol. So it sends the packet, starts the timer, stops itself and waits for the acknowledgement for the packet that it has sent. So now it is in this state, that is wait for acknowledgement 0. Okay. So now we are looking at all the positive actions that will happen, that can happen. So first is, okay, so we are at this state, wait for acknowledgement 0. Now it has received the packet. That means it receives a packet. It is not a corrupted packet, and it is having the correct sequence number. The acknowledgement is having the correct sequence number. When all these three conditions are met, then the timer is stopped. We had started the timer after sending the packet. So the timer is stopped at the sender side. Okay, and it goes to the next state where it is going to, you know, going to send a packet with sequence number 1. Okay, so it will wait for a call from the upper layer for making the packet, next packet. So this is the state that it will go to, that is wait for call 1 from above. And then the action that will be taken is basically there's a call and then the corresponding packet is created with the corresponding sequence number 1. Once it is sent, the timer is set and the sender side will simply wait for the corresponding acknowledgement. That is acknowledgement for sequence number 1 packet. Then again, once it receives a packet which is not corrupt and is having the correct sequence number as the acknowledgement in the acknowledgement packet, then it will stop the timer. Okay. So then this goes on, it will go to the next state, which is wait for call 0 from above. So this is all when everything is hunky-dory and there's no problem. Okay. Now we will see what happens if you started the timer but there was a timeout. So the sender was in this state. Okay, it was waiting for acknowledgement 0 and there was a timeout before it could receive any acknowledgement from the receiver's side. So it simply saw that there is a timeout. So what action it will take is it will simply retransmit the packet. So it retransmitted this packet, same packet with sequence number 0, and again it started the timer and was waiting in the same state for the acknowledgement. Okay, so this is what is going to happen at this point. Now there can be something else also that can happen. We have seen in the last FSMs that probably an acknowledgement packet is received, but either the packet is a corrupted packet or the sequence number in that is not the one that the sender was expecting. That is, the sender is waiting for the sequence number 0, for the acknowledgement of packet number 0, but it has received the acknowledgement for packet number 1. Okay, so in that case also it will simply wait for the acknowledgement of packet number 0 that was sent. Okay, now this is happening, this guy is happening before the timeout. Okay, if it is receiving something before the timeout, and it is not the correct one, so it's not doing any action at this point. It is simply waiting for the correct acknowledgement. Okay, only after the timeout it will send the it will resend the packet. Okay, all right. So now same thing in this case also, that is when you are waiting for call one from above. So if a packet is received, then if it is not correctly received, then you again take the same set of actions. Okay, all right. Now, okay. Hmm. All right. So basically, we are moving from this state. If there is a packet that has been received correctly, fine, no action. Wait for call from above. Then, if correct packet is has been sent, sorry, when there is a call from above for one, then of course you send the packet and then start the timer. The next is you wait for that acknowledgement. Again, if timeout happens, resend it, start the timer. And if the correct packet is received, so then you stop the timer. Okay. So same is here, that is wait for call from above. If the packet is received, then there's no action that has been taken. Okay. Now let's be a little more clear here and see that what are the different cases that can actually happen when it comes to RDT 3.0. Okay, so the first case is the best case, that is there is no loss of packets. So first is you send a packet with sequence number 0 and the receiver has received the packet with the same sequence number. So what it will do, it will simply send the acknowledgement, and the acknowledgement is also received at the sender's side. So what the sender will do, sender will send the next packet with the next sequence number. Then this will go on and on. So it sends the packet with the next sequence number 1. Then the packet is received at the receiver side. Then it sends the corresponding acknowledgement with that sequence number that it has uh, it has received the acknowledgement of packet number 1. That was the last packet that was received correctly at the receiver side, right? So again, this will go on. There is no loss in this scenario. Now, let's see a scenario where there actually is a packet loss. Okay, so let's see this case. So packet number 0 was transmitted over the medium. It was received at the receiver side. Receiver sent an acknowledgement for the same, and then the sender sent the next packet, that is packet number 1. So there is a packet loss in between. So packet 1 is lost in between. Now, sender is going to wait for the timeout. Okay. So once it faces a timeout and it does not receive anything from the receiver side, what it will see, what it will assume that the packet has been lost. So it will retransmit the packet. That is, it is resending the packet number 1 to the receiver side. Now packet number 1 is sent. It is received at the receiver side. Then again corresponding acknowledgements are being transferred and all is fine, right? So acknowledgement 1 is transferred. Then again the packet with the next sequence number, that is 0, is being transferred, and then it also reaches correctly at the receiver side, so on and so forth. Okay. What happens if an acknowledgement is going to be lost? Okay, in between. So packet was sent, packet number 0. It is received at the receiver side. It sends an acknowledgement of the same packet. Then the next packet, that is packet 1, is sent from the sender's side. It is received at the receiver side. The receiver prepares an acknowledgement and transmits it over the medium, but the acknowledgement is lost in the path. So sender was waiting. So until timeout, it will wait. And then once it does not receive the acknowledgement, it will simply resend the packet. So now packet 1 has been resent again. So what the receiver will do? the receiver will simply find out that okay, there is a duplicate that I have received. So what it will do, it will send the last packet that it has acknowledgement for the last packet that it has received correctly, and that is for packet number one, right? So it will send an acknowledgement for packet number one, and then it will transmit it over the medium. Now, when the sender receives this acknowledgement, at this point, the sender gets to know that okay, packet received successfully, and then it will send the next packet with the next sequence number. Now, next case is that premature timeout or delayed acknowledgement. Okay, so now what happens here? Let's see. Sender is sending a packet with sequence number 0. It was received at the receiver's side, and then the corresponding acknowledgement was sent. Once the acknowledgement is received, sender sends packet number 1, starts the timer. Packet 1 reaches the receiver's side, sends an acknowledgement. But by the time the acknowledgement could be received at the sender's side, the timeout has happened. Okay, so what happens if the timeout happens? It will simply resend the packet again. So it resends the packet 1. Now once it has sent the packet, now just after that, the acknowledgement for the same packet has been received at the sender's side. So receiver gets a duplicate packet anyways, okay, because the packet was anyways transferred. So it again sends the acknowledgement for the same packet to the sender, okay, because once it resends this packet, again there will be a timer, okay. So then what happens? See, once this packet is resent, there will again be a timer, right? So now at this point, please take a look at this. Here, this part is a little tricky here. So once the timer is out, packet 1 is sent, packet 1 is received at the receiver side, it detects a duplicate. It sends an acknowledgement. Now remember, there was a previous acknowledgement also, which was just delayed simply. So it reaches before the timeout of the second time transmission of packet number 1. So once that packet's acknowledgement is received, what the sender is thinking, it is thinking that okay, I sent the second packet, maybe that is the acknowledgement for this one. Whatever, I am not going to think much on it because I don't know what it is. So what I'll do, I'll simply send the packet with the next sequence number. So that's what the sender is going to do now. It is simply going to send the sequence number for packet number 0. Okay, so it will send the packet and it will be received, and then the receiver will send the acknowledgement number 1. But before that, what's happening? The acknowledgement for this packet will come from the receiver, and now the sender is basically in what state? Waiting for acknowledgement of packet 0. It will wait for acknowledgement of packet. This sender is waiting for acknowledgement of packet 0, but it has sent that it has received the acknowledgement for packet number 1. So again, it will think that okay, maybe something is wrong in between. Okay, so yeah. So this is the issue that will happen when it comes to premature timeout or maybe delayed acknowledgement. Okay, yeah. So that's what happens when this acknowledgement is received. Then next packet will be again transferred. So what have we learned in the previous FSM? If you remember that, in the previous slide, when there was such a scenario that a duplicate acknowledgement is being received, then in that case, there's no action that is being taken. Okay, so take a look at this again when you go back or when you look at the slides once more. So you will find that there's no action that is being taken. So what does this mean? The sender is basically going to ignore this acknowledgement that it has received at this point. Okay, because now it is not waiting for acknowledgement for packet 1. It is received that, It is only waiting for acknowledgement for packet 0, and it will wait for that simply. Okay. So now we are going to look at that how this RDT 3.0 performs. Okay. So this, we know that this is known as this category of RDT protocols. This is known as stop at mid protocols. Okay. So we define certain metrics. First is U sender, which is basically the utilization or the fraction of time the sender is busy sending a packet. So let's see an example. So suppose you have a 1 Gbps link capacity in your medium and 15 milliseconds of propagation delay, and the size of the packet is of 8,000 bits. Okay, so what do we know? How do we find out what is the time taken to transmit? So the time taken to transmit the packet would be, simply, 8,000 bits per sorry, 8,000 bit packet divided by the link capacity, right? And this gives you 8 microseconds transmission delay. All right. We have a propagation delay of 15 milliseconds, and we now have a transmission delay of 8 microseconds. Now, how would this work out? So first bit of the packet, when it will be transmitted from the sender side, okay, from then it will take, what was the value? 8 microseconds, right? So it will take 8 microseconds or just the transmission delay to send the entire packet over the medium. So first bit of packet is received at the receiver until the last bit of packet is received. Until the last bit of packet is received, the receiver will not send an acknowledgement. It will send the acknowledgement only after the last bit of packet has arrived. Okay. So once that is done, then the acknowledgement will be sent from the receiver side, and the acknowledgement is received at the sender side. Okay. Now this time, we had seen earlier also, this time that is taken from sending the packet, like the full transmission of the packet, and then the reception of the acknowledgement. So this entire time will be considered as one round trip time, or RTT. So the total time that is required, or the sender basically waits for a total time of the transmission delay plus a round trip time before it can send another packet. Okay. So the sender is sending a packet, and then after that it is waiting for its transmission plus a round trip time just for waiting for the acknowledgement. Okay. Now, all right. So let's see what is the utilization that we are getting here. All right. So the utilization is basically that, the transmission delay that we are getting divided by the total time that is being taken to actually receive the acknowledgement. Okay, or for the entire transmission, this entire sequence of steps, that is transmission of packets plus reception of the acknowledgement. So that's the total time, RTT plus L by R. So according to what we had taken as an example, so it comes as, 8 microseconds was that value, and the round trip time has been considered as 30 plus, this point 008. So it comes out as point 0.0027. Okay. So basically the utilization on this RDT 3.0's performance is quite bad, because there's, you know, the utilization that of the resource that has been that is there for the sender, that is very less. Okay. So the performance becomes very bad because it is simply waiting for an acknowledgement after sending a packet. So until that time, the resource is not being used at all. So it is simply like this, that, you want to send a, so this is a stop and wait operation that's happening here. So you want to send a packet from one end of a country to another end of the country. So from west side of US to the east side of it. So if you just do a stop and wait, it is going to take so much of time, right? Given more and more propagation delay, if you have, given the entire distance that it has to travel, it is going to increase more and more. Okay, so that's one issue. All right, so how can we overcome this? So we can overcome such scenarios. You must have read by now that pipelining is one idea that can be used to overcome any such waiting kind of a scenario. Okay, so the same idea of pipelining is being used here. Okay, so what will it, or how will it help? So pipelining will basically allow the sender to send multiple packets at a time. Okay, so those packets which have not been acknowledged yet. So a sender can simply send a few packets until it gets some acknowledgements from corresponding to those packets. Okay, so what will we need? Now we cannot work with only 0 and 1. We need a range of sequence numbers, right? And what else do we need? We need a buffer. Okay, we need a buffer because we are sending the packets. Those will be received at the receiver side, but the sender also needs the acknowledgements correspondingly. Okay, so let's see how it will work out. So this is how the pipelining thing is working. So if you can see in the next in this figure B, where a large number of packets are being sent over the medium, and then corresponding acknowledgement packets are also sent one by one, and the sender is not waiting for acknowledgement of any of the packets. So let's see how it increases the utilization. So first is, as we had seen, that the first bit is transmitted at time t equals to 0, and the last bit of the packet is transmitted after its transmission delay, that is L by R, given by L by R. Now here let us suppose that 3 packets can be transferred at a time. That means one by one they can be transferred in the pipeline. So first packet is transferred. Now after that, once its transmission is done, the second packet will be transferred, and then the third packet will be transferred. Now meanwhile, once the last bit of packet 1 is received at the receiver side, it will simply send an acknowledgement. Okay. Then again, once the last bit of second packet is being received, then again corresponding acknowledgement will be received. Okay. So correspondingly, the acknowledgements are also are being received at the sender side. Okay. So this is how it is working. So now let's see how the utilization is going to work. So for packet number 1, we do have simply L by R plus RTT. So that is this entire block. But imagine that in this one we also could send 2 more packets. Okay, the utilization should increase by now. So how will the utilization will increase now? See, earlier it was only L by R, now it is 3 L by R because 3 packets are being sent within the same time instance, right? So sorry, within the same time gap. So that means RTT plus L by R, in this time interval you can send 3 packets, which basically increases your utilization. All right. So now, see, earlier we were having only this, stopping and waiting. Now we have acknowledgements which are cumulatively coming and packets which are cumulatively being transferred. Okay. So we must have some kind of a protocol which will take care of such a scenario. Okay. So this is when we get into this protocol, which is known as go back N protocol. Okay. So go back N protocol is what? That means the sender will have the feature that it will be able to send up to a particular number of packets. That means up to probably N packets. It has been given here. Okay. So N packets it can send without getting them acknowledged. up to n packets it can send. Okay. So it must have a window kind of a thing, that is, so we were talking about having a buffer, right? So we must have a window kind of a thing which is similar to a buffer that will simply say that, okay, within this window size, this is size n, there are packets which are sent, which have been acknowledged, which have not been acknowledged, etc. So we will see how it works out. So the green ones, the green packets, they are basically the ones which have already been acknowledged and has been given here. Okay. Some packets which are sent but are not yet acknowledged, they are represented as yellow bars. The packets are not yet sent but are to be sent. Those are the blue bars, and this is the white one which is still not usable. Okay. Now we are saying that we will have a window. Okay. So window means within this sorry, within this interval, whatever packets fall in this, those packets can be transmitted even if they have um, not been acknowledged yet. So this is up to this part, that is the last green part, the packets were acknowledged. Okay, this is at the sender's side. Now the next packet, that is send base, that is from where you are going to start transmission in the next time instance. So send base is the one where the first packet which has not yet been acknowledged is there. So that is the one. And then after a sequence of such unacknowledged packets which have already been sent, there's another packet which another set of packets which are given by these usable but not sent packets. Okay, so here it will start with the next sequence number, because just before that, until this yellow one, you have already sent the packets with these sequence numbers. Okay, so your send base had started from this part of the window, and you had sent the packets with up to this sequence number. Now the next sequence number, for which sequence number of packet which has to be sent now, starts with this one pointed by this pointer, that is next sequence number. Okay, now as and when the packets will be acknowledged, the windows will basically move towards this side, right? Because those will be acknowledged. So again, these next packets will now, if they become suitable or usable for transmission, then again it's basically a moving window. So the moving window thing we'll see later on. Let's see first that how this go back n works. So this is a cumulative acknowledgement scenario. We have already seen it, that too many packets, sorry, a number of packets are being sent. Here it is of size n. So up to n sequence number packets can be sent, and the corresponding acknowledgements can be received cumulatively. Okay. Now see, that's what I was talking about, that once a packet's acknowledgement is being received, then the window is moved forward, okay, to begin at the next sequence number, which is n plus 1. So if the last sequence number for last sequence number packet whose sequence number is n and its acknowledgement is received, only then the window will be moved forward by plus 1, which is here, n plus 1. Okay. So timer would be timer will be for the oldest packet that was being transferred first. Okay. So the oldest timer will start for the oldest in-flight packet, and timeout will be whenever there is a timeout, then the entire packet n, that is retransmit packet n and all higher sequence number packets in the window. Okay, so whatever packets timer is out, that packet and all the next sequence number packets in the window that were already sent, they will again be resent. Okay, So let's see the example. We need to see an example here. But before that, there's this slide for the receiver. So let's see what the receiver also does. So receiver, of course, here also we are only having acknowledgements from the side of the receiver. So whenever a receiver, of course, if it is receiving a correct packet, it will send a acknowledgement. Okay. But what it will give in the acknowledgement, it will have the highest in order sequence number. Okay. So that means whatever sequence number packets it has received, out of which one is having the highest sequence number in order, that one only it will send as the acknowledgement, as the sequence number in the acknowledgement. Okay. So this may receive in duplicate acknowledgements, of course, and then, okay, what the receiver will require, it will require to remember what was the base sequence number that it had to receive. Okay, so this may sound all a little confusing. It will become very clear with an example. So let's just see what happens. So if the receiver receives an out of order packet, then it can either discard the packet or it can buffer the packet depending upon what kind of protocol you are using. Okay, all right. So this is the receiver base. Okay, this is what the receiver is going to expect. So these green ones are the received packet and they have been acknowledged also. These packets have not been, these are just not received yet. And the out of order packets, that is packets which have been received but they are not acknowledged yet. Okay, so this is where, that is, this is the expected sequence number that is being expected from the receiver side, and it is pointed as receive base. Okay, others which have been which have been received, they have not been acknowledged yet because they are all out of order. So let's see how it works with an example. So this is a window. This blue block is a window. That means your window is having n equals to 4. 4 packets can be sent at a time. Now, the sequence numbers are moving from 0 to 8. Okay. So at the sender side, what's happening? 0, 1, 2, 3. These 4 packets have been sent from the sender side, and then it is basically waiting for an acknowledgement. Okay. What's happening at the receiver side? It has received packet 0, it has sent the corresponding acknowledgement. Same for packet 1 also. But in between, packet 2 got lost. But packet 3 has been received. Okay. So what the receiver will do? See, this one we had seen that it depends on implementation decision. So according to the go back end protocol, what happens? If it receives a packet, okay, even if it's a correct packet, but it is not of the sequence that is being expected by the receiver. Receiver is expecting packet number 2, but it has received packet number 3. So it will discard the packet, and what it will do, it will send the acknowledgement of the last packet it had received correctly. That means it will send the acknowledgement of packet number 1. Okay, so these are the corresponding acknowledgements that are being received at the sender side. So first let us see, when the sender receives acknowledgement 0. So what we know, when a correct acknowledgement is being received at the receiver side, it will simply move the window forward by 1, right? So it is moving the window. Yeah. Then again, next packet, the window again gets moved. Okay. And of course, the next packet is also being sent. That is send packet number 4 and send packet number 5. Now, what happens here? So here, um, acknowledgement for packet number 1 is received. So the sender side knows that receive acknowledgement for packet number 1 has already been received. So what it will do, it is simply duplicate the acknowledgements. Sorry, ignore the duplicate acknowledgements. But what's happening at this side? Because sender has sent packet number 4 and packet number 5 already. But at the receiver side, what's happening? Receiver is still waiting for packet with sequence number 2. So what it will do? It will simply discard the packet and resend the same acknowledgement. That means it will resend acknowledgement for packet number 1. Okay. So within this, what happens? For packet number 2, by this time, the timeout goes off. Once the timeout goes off, only then again the sender will realize that okay, this packet's timeout has gone. So that means this packet and all the subsequent packets, they may or may not have been received correctly, right? So what it will do? It will simply resend the packets after 2 and including 2. So 2, 3, 4, 5. These will be again transmitted. Okay, so you can see these are again transmitted. Corresponding acknowledgements are also being received at the receiver side. So you can see, corresponding acknowledgements are also being sent by the receiver side. So you can see that there is a lot of duplicates that is going on. There's a lot of loss of resources also that is going on because packets are getting discarded even if they are being received correctly, right? So we have to think of something that is better than this. Okay, so this protocol is known as selective repeat protocol. So I will stop the class here today because we are out of time now. But in the next class, I will start with the selective repeat protocol. Okay, so if you have any questions from today's class,